All right, so in this question, we have an unknown weak base, and we know that its concentration is 0.170 molar, and we measure the pH to be 9.42, and based on that pH and the concentration, we want to calculate the ionization constant, the Kb of the base. Also, this is a question where you will be given a different pH than 9.42, but the method of solution will be the same as what I present here. All right, so this is another rice table problem. So we'll set up our rice table. Okay. And in the rice table, we have the reaction there at the top. And in this reaction, what we have is just some base, we'll just call that B, and it's going to react with a water molecule. And it's a weak base, so it will do that in a reversible way. And it's going to rip a hydrogen off the water molecule to become BH plus, the conjugate acid. And then what's left over on the water, after I take a hydrogen off here, is a hydroxide ion. Okay, so each one of these gets their own column in the table. And we are told that the concentration of this base is 0.170. Now that's an initial concentration of the base. Okay, and we know that the water, because it's a pure liquid, it doesn't show up in the equilibrium constant expression, so we don't mess with it in the table. And the initial concentrations of these two guys, these two products, is 0. This is a pre-equilibrium concentration. So we know that nature's not going to be satisfied with this situation because it's a reversible reaction. There should be some of every thing in the reaction mixture. So I'm going to produce some BH plus, and I'm going to produce some hydroxide ions, so plus X and plus X. Well, it came from this base reacting with the water, so I can do a minus X over on that side. So then I just bring the columns down, so 0.170 minus X, X, and X. Okay. Now, the other important piece of information I have is the fact that the pH is equal to 9.42. All right, so if the pH is equal to 9.42, and we know that the pH is related to the hydronium ion concentration, but I don't have hydronium ions in this chemical reaction. I have hydroxide ions. So what would be useful is if I can find out what the pOH is. And I know that there's a relationship between pH and pOH. The sum of the two always equals 14. So the pH is going to be 14 minus 9.42, which is 4.58. Okay, so that's the pOH. And the other thing I know about pOH is that it's equal to the negative log, the negative log of the hydroxide ion concentration. Okay, so therefore, if I want to find the hydroxide ion concentration, it's equal to 10 raised to the power of the negative pOH. Okay, so in this case, that means that the hydroxide ion concentration is equal to 10 raised to the power of negative 4.58. And if you plug that into your calculator, it will tell you that that equals 2.63 times 10 to the minus 5 molar. All right? And the other nice thing about that number, that equilibrium hydroxide ion concentration, is that it's equal to X. Okay? So now I know X, and I'm going to use X to calculate the Kb. Because the Kb, if I were to write an expression for Kb, it's just like any other equilibrium constant. It's the concentration of each product times each other, raised to the power of their balancing coefficients, which is 1 in each case here. And you divide that by the concentration of the reactant. And we don't put the water in the expression because it's a pure liquid. Well, from the equilibrium row on the rice table, I can just substitute in the terms. And so the concentration of BH plus is X, and the concentration of OH minus is X, and that's over the concentration of the base at equilibrium, which is 0.170 minus X. Well, now I know a value for X, so I can just substitute that each place, right? And so I can do the calculation now. So it becomes 2.63 times 10 to the minus 5 squared over 0.170 minus 0.263, pardon me, 1.70 minus 2.63 times 10 to the minus 5. Okay, well, if you do that math, that comes out to be 4.07 times 10 to the minus 9. So that is the answer to the question. That is the Kb of this unknown base.